Okay, so yeah, I think this week, like today's lecture and tomorrow's lecture, that's the end of the semester. Okay, and yeah, so what we discussed yesterday, just a brief recap what we discussed about. So we are talking about statistics, and the main goal, or let's say the subject of statistics, it is about statistic. And what is a statistic? Okay, so if you recall, we have a population here. Population means a large data set, although large is relative. And then we have a sample. So it's a random sample. We spoke about the random sample. And the idea is, and this is the population. And the idea is we want to say, we want to make some statements about the population. Okay, so we want to make certain statements about the population. Okay, using our random sample. Now the question is how the random sample is produced. That's a different separate issue which we are not discussing here. But if the random sample is given to us, then the question is, okay, how to make certain statements about population from the random sample. So what we started talking about is like, okay, let's say x1, x2, dot be a random sample. So they are denoting the random variables. They are realizations of an underlying random variable x, which corresponds to the population. So this is x. We are measuring something, and that after this measurement, you got the data. And now this x1, x2, xn, they are IID. Okay, and so they have the same distribution as x. Okay, and yeah, and then what is a statistic? A statistic is nothing but a function of this x1, x2, xn. So whatever the distribution is, if we assume that, okay, the PDF of this x is some f of, let's say, x theta. So we are writing a semicolon here because, as we said, the theta will play a role because theta we do not know. We may have a guess about the distribution. We do not know the value of theta. Even if we know what is the PDF, then the question is, what can we say about x1, x2, xn? Or maybe if we take any function of this x1, x2, xn, could be any function of x1, x2, xn, like x1 square plus dot 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 plus xn square. This could be a function. Or we said something about x bar, like the sample mean. We defined what is called sample variance. So these are statistics, and they are independent of theta. Okay, so that was the basic definition of statistic. That when we say about statistic, it is kind of a function of this x1, x2, xn, which is independent of this theta. Because in certain situations, as we have discussed, the theta is not known, but we have a guess about the function, the PDF. It could be a very standard PDF like normal, Poisson, or whatever it is. Okay. Now, yeah. So in practice, what we get is these are not random variables, the random sample, but this is a sample data. So x1, x2, dot 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 xn. So we get n number of data points, okay, which are I'm denoting as small x1, small x2, dot 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 small xn. Then the idea is, okay, so if I consider a statistic, okay, like this one, x1 square plus xn square, then from the sample data, I can consider small x1 square, small x2 square, dot dot dot, plus small xn square, okay? Or if I take a sample mean, okay, so this is sum over xi, equal to 1 to n, divided by n, 1 by n, yeah, so multiplied by 1 by n. So this is what is sample mean. So if we have a sample data, small x1, small x2, small xn, then I can replace this capital Xi by small xi, and I would get a number. I'll get a value. Similar thing I can do it for the sample variance. And then the idea was, okay, and we have seen some theorems, so which we talked about, like sampling distribution. So sampling distribution is what? This is a PDF, density function of some statistic. In fact, we spoke about the sample variance, sample mean, and we have seen like if X, this capital X is following certain standard distribution like normal, then we can, and if we consider different kind of statistics like this, okay, or this, then what are the distributions of the statistics? What are the PDFs of the statistics? So those are called sampling distributions, and we have studied different kind of distribution. Like specifically, we focused on chi-square distribution and T distribution and F distribution. Okay, so because they arise frequently in different kind of study, and they have nice analytical formulas. Although, I mean, it is of course an important question how somebody can derive those analytical formulas. Okay, so that is the job of statisticians or mathematicians. But again, we are studying this, so those distributions are discovered more than 100 years ago. But anyway, so we are studying it now. Anyway, this is how science progresses. So once you have this PDF, if you have a guess about this PDF, suppose it is not known, PDF of this X, then the question is how do we estimate this theta? So we started talking about what is called estimation theory or theory of estimation. Okay, so the main problem here is estimate theta, okay, from the sample data, from the sampled data. So basically, I have this small x1, small x2, small xn. From those values, okay, I want to define a number which can estimate this unknown parameter theta. Okay, and we said, okay, from the sample data, small x and small x, then I can define a statistic like x bar or s square, okay, or this one, okay, or anything, any statistic I consider. Okay, then the question will be, if I put those values, if I replace those capital Xi by the small xi, will it estimate theta? Or what should be a statistic, okay, which will determine or which will estimate this unknown parameter theta? So for that, I mean, just the question is then, so here the estimation theory or the theory of estimation, the question is then ultimately find a statistic, okay, that can estimate the unknown parameter theta, the unknown parameter theta. Oh, parameter theta. Okay, but when I'm saying find a statistic, so I'm assuming that I know. So here, under the assumption, under the guess, or let's say on the assumption about fx theta. That means what I'm saying is theta is not known, but I have an idea about f. It could be normal, it could be something else. Let's say it is a standard distribution. I know the formula, okay, of this PDF, but I do not know exactly what values of theta this entire data set is produced. Okay, so my goal is then find this value of theta from this random sample. So first of all, I said here we are not talking about what happens in practice, because as we said before, like in practice, in real life, the problems are really, really hard, and you need to design a solution which is problem specific. I mean, it depends on the problem, how the data set is produced, and accordingly you can define a statistic. But here, what we can do in this course is like, okay, suppose it is very like this is normal kind of. So if I make this kind of assumption, then our job is, okay, what is the statistic? So in normal, for example, or any other distribution which has a very nice formula, okay, very simpler formula. Okay, this f has a very nice form, f has very simpler form. Then the question would be, okay, so find a statistic. Now we need a method to find a statistic. Since we are doing a theoretical study here, we said, okay, there are many ways to find the statistic, and we will say we will discuss only two methods. One is moment method, okay, method of moments. It is known as MOM, method of moments. Okay, and another one is, okay, we'll talk about that. But what is the principle? Okay, what is the principle of what is the principle of MOM, the method of moments. Okay, we said the method of moments. So the idea here is you have to choose a value for this unknown parameter theta such that the observed data, that means the sample data, have the same moment as the population. So the idea is if mi, so what are the moments? So this is e to expectation of x to the power k, where x is the distribution and k is a positive number. Okay, if we have, let's say, one parameter, so I'll only consider the k equal to 1. If I have two parameters, I'll consider k equal to 2 and so on. So I have sample data, from that I can calculate the moment. So for example, I can calculate the expectation of this value. So I can take the average of these values, and then I can equate it with this x. Then if you have two parameters, then I'll take these two equations, okay? And these are obtained from the sample data, like using the formula, okay, like expectation. So it will be 1 by n xi, I mean sum of this one. If it is m2, it will be sum of this xi square 1 by n and so on. So yeah, so depending on how many parameters I have for the PDF, okay, I can take those many equations and I can solve them to find an estimate. So to find the statistic, okay, for the estimator, let's say the statistic which will estimate my unknown parameters. Okay. In fact, what we have done in this course is like all this gamma, beta, I mean, are normal. So we have maximum 2 parameters. Okay, we did not study more than 2 parameters. Like we did not study any PDF which has more than 2 parameters. In fact, we have studied only one. I would say that is bivariate normal, which has 4 parameters, and that's the end of it. We did not study more than 4 parameters. Anyway, so this is a method to find the estimator. Okay, and this is the idea. This is the principle. And then I said I introduced another method which is called maximum likelihood method. Or yeah, so this is what we introduced last day towards the end. Maximum likelihood method. So MLM, or just people say LM method. Okay, ML method. Yeah. So this is okay. This was discovered in 1922, so exactly almost 100 years back. Okay, so here the idea is if I know
Sir,
this fx theta, yeah.
sir, yes, sir. Sir, for the case of like movement method, MOM method, sir, like if we have one variable, like only one parameter theta. So, sir, so for this we will use only M1.
Yeah,
But, sir,
yeah.
how can we confirm that like the M2 and M3 of the sample and population will be same?
No, I'm saying, so yeah, that's a very good question. So I'm not assuming that they are same. What I'm saying is that I need only 2 parameters. So see, the question is, if you start considering all possible moments, where do you stop? Right? Whether I will take 2 or 3 or 4 or 10 or 100, doesn't matter, right? Here, how many equations I'll consider? So I want to consider number of equations to be equal to number of parameters. So it's like a linear kind of a system. Okay. So number of variables is equal to number of equations. So since I have only one parameter to estimate, I'll consider only one equation. So I'm not guaranteeing that the second moment also will be same. Okay. But what I'm assuming here is the first moment is the same, and I'll calculate the value. Then if I have 2 parameters, then there will be 2 equations. So I'll assume the parameters 2. I mean, this is what the method says. Okay. I'm not commenting about, so because okay, today probably we'll talk about how good the method is. If I change my method, whether I'll get the same estimator or not. For example, I said last day also that if you take this, let's say uniform distribution. So if x is uniform, okay, x is suppose it's a uniform, then we said okay, uniform means I discussed about this x theta is equal to 1 by theta when it is from 0 less than x less than theta and 0 otherwise. Then if I estimate theta, estimator for theta was actually 2 times x bar. Okay, x bar is the sample. This is the estimator for theta. Now the question is, if I pick this particular example and if I apply another method to estimate the same theta, will I get the same estimator or not? That is again a question. Okay, so it is So as I said before, it is a study of common sense. It is not like something. It is very problem specific. There is no only single method which will give you the best way, or that's the only way to calculate the value. Okay. So here the idea is, in this method we are assuming k equations because I have k parameters. That's it. So I'm not commenting that if you take more than k equations, k could be 1, 2 depending on the number of parameters. Okay, that will give you a better estimation, or that will give you a better estimator. Okay, I'm not commenting on that. So this is the method, and this is it may not guarantee, of course, it may not guarantee that the rest of the moments are same. But I am assuming, the method is assuming that at least those moments are same, which equals to the number of the parameters. So I'm considering number of equations as number of parameters. Did I make any sense?
Yes, sir. Yes, sir. I got your point.
Yeah. So yeah, so you can you can consider that, but then again you will have overdetermined system. So I mean, we should not stay. I mean, the problem is, I mean, there are many things here. I'm just skipping because we don't have that much time. I mean, this entire method can take, I mean, at least 1 hour to discuss, but we don't have that much time. So I'm just skipping many things. But just to give you a brief idea, like what is it? Okay. So yeah, so the problem will be like, even if we take more than k equations, let's say I have one parameter, I take 10 equations. That's an overdetermined system. Okay, then question will be, how do you solve such a system? I mean, you can start with a problem. Let's say normal distribution. You have 2 parameters at least. It's a very nice thing. Let's say you make five moments to be equal, and then see like how I can find the estimator. Okay, and how to solve. You have 2 parameters and 5 equations to be satisfied. And how to solve this problem? So there are different challenges. There are different things. Okay, only things will be clear when you get into it, and when you try to see like what happens if I do that. Okay, that's how science progresses. Like our maths, we do maths. Okay, so I mean, your question is very good question. I mean, your question is very nice. That's very good, valid question. And I think you can consider an example and start doing it and see what is coming up. Okay, for example, you can start doing this and take 2 or 3 equations, like 2 or 3 moments, and then see whether the rest of the moments are same or they are different, or what is happening actually. Okay, you can do that. Yeah. Okay, then we started talking about maximum likelihood method. And in this method, okay, so whatever, so again, the assumption is like this is known. And then we define what a function, which is known as a likelihood function. Okay, this is a likelihood function. And here the procedure is like, okay, first we consider this function. So there is a parameter theta, or there are parameters thetas. Okay, and the likelihood function is like L of theta is the product of, because you have n random sample x1, x2, let's dot n. So for each of this xi is following x. Okay, the same distribution on x. So the distribution of this entire sample PDF, and the PDF of this x1, x2, xn as a, I mean, or you can say joint PDF of this random sample, or this random vector of random variables, because each of these is a random variable. So I can consider the joint PDF. But joint PDF is again the product of the PDFs because they're all independent. So that's how I'm defining L theta. So here theta is same because they're all following x, but x1, this x1, x2. So there are different values for this x1, x2, x2. So what I'm saying is these are nothing but the product of this individual. And this is xi, individual PDF, and this is I equal to 1 to n. And this is what we call the likelihood function. And what is the idea? Idea here is that I will estimate, I'll define my estimator as the estimator. So theta cap is my estimator. This is the notation I'm using. I mean, this is standard notation, which will give me the max value of this L theta. So this theta is in my parameter space. Parameter space means these are the admissible values of theta. For example, if I consider normal, then the standard deviation or variance is always positive. Okay, so this is like, if I just consider, so this we talked about it. So it is like upper plane. Okay, that is the parameter space. And then we are writing arc of this. That means I am not interested about the maximum of this. Of course, I'm interested, but I want to find out that theta which will maximize this. So I'm talking about the argument of this function, which is theta. So I want to find theta, which will maximize the value of this L theta. And this is an optimization problem. In fact, you'll see later on if you do kind of a project or some machine learning or anything related to statistics, there is a role of statistics, let's say. I mean, most of the practical problems in this world, real world problems, okay, they end up with an optimization problem because ultimately you have many choices for your solution, but you want to find the best choice. And it is, of course, problem specific. And see here, this problem is not simple. This is a hard problem. I mean, let me just tell you one line or two lines about why this is hard. See, see, what have you studied about optimization in your entire life? We have studied like we have one parameter or two parameters, let's say. Okay. We have a very nice thing, like let's say we have, even if we, because in math one, we have studied two parameters problem. So we have a very nice thing, like let's say this is a rectangle, this is my domain. These are all x, y, these are the points, and there is some kind of a function. Okay, so this is a kind of a function defined on this entire domain, let's say. Okay, this entire domain, this function is defined. And then, so this is surface, okay, I'm talking about surface. So then, then you want to find the maximum value of this. But these are all nice things. Why the problem could be difficult? This problem could be difficult because of the parameter space. Because the parameter space need not be a nice rectangular form. Parameter space could be anything. That's a real life problem. So difficult. It could be any subset of, if it is, even if it is two parameter, it could be any subset like this. Because suppose you are only considering admissible values of this theta. Maybe there are some parameters, let's say theta 1 and theta 2. Theta 1 can take only integer value, let's say. And theta 2 can take some parameters value from let's say, circle. So you have very discrete optimization problem in that case. Or suppose is theta, there are two parameters, theta 1, theta 2. Theta can be in a rectangle or on a rectangle, and theta 2 can be on a circle. So then the problem becomes very, very complicated when you have this parameter space. The geometry of this parameters is very complicated, let's say. And this is always a hard problem, how to find an optimization. Then all these are methods, whichever you know, let's say, what do you do if you, even if you have two matter? For a single parameter, you can take the derivative, put it to 0, take the second derivative, and find out its maximum value. Third is, okay, if you have two parameters, so you can take the partial derivatives, you can find where the partial derivatives are 0, and then you can check the Jacobian, and you can find out what is the whether it is maximum, I mean, which theta will give you the maximum. But in general, in any way, so I mean, there are a lot of complicated things will appear. I mean, there are a lot of complicated things when we consider this as a general problem. Okay, so that's a real life problems are really, really hard to solve. So I mean, this optimization problem itself will take a lot of time to decide like which method would solve this problem. Okay, depending on of course what is my parameter spaces. So in general, this is a hard problem, but in this code, this is not hard. This is very simple. I have many probably one parameter, two parameter functions like likelihood function. And what we can do, okay, this is the method. Method is, okay, you have this x1, x2, xn. So first, you obtain this, whatever the random sample is, this is x1. These are known to you. This is random. Whatever, however way you have obtained doesn't matter. Suppose you have this random sample, okay? And then what you do is, so you consider this L theta. Then third one is find the expression, find theta which maximize this, which maximize L theta, okay? And then you do what? Then you replace theta, okay? Replace theta by the function form, the theta hat, okay? To obtain the maximum likelihood estimator for theta, okay? And then you can find out after you find the statistic estimator, then you can again put a sample data, then assign the observed value, assign the observed values or the sample data to the estimator and find out the estimate and for theta and find estimate the value of theta. Okay, assign the sample data into this into the estimator. So this is how the method goes. I mean, this is very simple. It's not very difficult. Let us see an example. Okay. Suppose I have a random sample, and this x theta, let's say, is very simple like this: 1 minus theta x. Okay, maybe I will pick. Okay, let me just say this since I have written this, because we don't have much time to talk about many examples, but at least we need to see 1 or 2 examples. This is otherwise. Okay, and so this is my x and theta, and let's say x1, x2, xn. This is the random sample. So they are all following x, and x has a PD of this one. Then the question is what? Find theta hat. So you want to find an estimator for theta, okay, using ML, the maximum likelihood method. Okay, so what you do first of all is let's say solution is L theta. You first define L theta. So L theta is what? It's the product of I equal to 1 to n f of xi and then theta. So this is a product form, okay, where there is an exponential term here. So probably you can take log both sides, then it will be simpler. Log of L theta is the log of this entire thing, which is what? This will be just to take the log, this will be log of f of xi theta. And once you do that, so okay, I equal to 1 to n, and then this will be nothing but n log of 1 minus theta sum over log of xi. I mean, you just expand it. I mean, put this x theta here. Okay, so this is the product form. So log of this, so log of this plus log of this plus theta minus theta will come out. So you'll have log of xi. That's how you get here. Okay, this one. Now what you can do, this is my function. Then you want to optimize this or maximize this. Then what you do is you take a derivative both sides, log theta, log L theta. So basically this is dd theta of this expression. So if you do that, what do you get? N. Now log means 1 minus theta minus theta. If you take with respect to theta, it is 1. So it is log of xi. So you know this sample data, okay? So don't worry about that. You know all this sample data. They are the fixed values. Now, if you want to maximize this, in order to maximize, what you do is you put that to be equal to 0. And to maximize, you put that to be equal to 0. So dd theta of, so this entire term, let's say equal to 0. Or log of theta to be equal to 0. So what does it? 1 minus, yes.
Sir, differentiation of log 1 minus theta will be minus 1 upon 1 minus theta. So
Oh yeah, you are
here
right. You are right. So here it will be minus. Yeah, sure. Okay, so then my equation changes. So anyway, so if you do that, then minus this equal to 0. So okay, so then this will be minus 1 by n sum over I equal to 1 to n log of xi. Yeah. Okay, so this is what this means: 1 by 1 minus theta minus 1 by this. So I can write it as this is, now see here, this is like average of log xi. Okay, I equal to 1 to n. So average values of log of xi. So this is nothing but minus remains log of x and then bar. So this is my notation for the average value for the sample mean. This is this one. So from here I can get theta is equal to 1 plus 1 by log x bar. So what is my theta bar? So theta hat. This is 1 plus 1 by log x and then bar of this. The sample mean of the log value of the sample data will estimate my theta. So this is my estimator using this ML method, maximum likelihood method. Okay. So this is very simple. I mean, you just have this function, then take the L theta, take the log, and then do the derivative, and it's simple as that. So we get this one. So it is not, so see now here from this function at least estimator, you can see that you cannot guess what is this function. You have to really solve this problem. Okay. So at least when this function is nice, function is the PDF, fx theta is nice, then you have to do this little bit of algebra to calculate. I mean, this is a little bit of calculation, I would say, to calculate to find out what is the estimate of theta hat. Now let us see another problem, which I said I will do. So, which is like if you take uniform. So this is my uniform distribution 1 by theta. Let's say if 0 is less than x less than theta and 0 otherwise. This is my, and we have done this. We have found out estimator for theta using our momentum method, and we have seen that 2 times x bar, 2 times capital X bar, okay, is the estimator for theta. Now let us find the estimator. Question here is find theta hat, okay, using ML, the maximum likelihood method. If you do that, what do you see? So again, first of all, you compute L theta, which is product of I equal to, suppose we have n random samples, so f of x theta, xi theta. So this is nothing but 1 by theta here, okay? It just depends on theta, okay? There is no role of xi here, okay? I mean, xi means only when this xi is lying between 0 to theta, of course. So yeah, so here I equal to 1 to n, 1 by theta if the theta is bigger than xi, okay, or I would say 0 less than xi less than theta, for all I equal to 1 to depending on n. So this is basically 1 by theta to the power n. Okay. Now what is the parameter space here? Parameter space here is parameter space for L theta. What is that theta? All those numbers such that if max of this theta is less than, of course, infinity. So theta has to be this one, okay, bigger than the max, because they have to be, theta has to be bigger than all this xi, so it has to be maximum of this, all this. So this is basically the parameter space here is this x max, the max sample data, okay, and then up to infinity. So you want to maximize this L theta on this space, okay. Now see here, depending on the sample data, you get your parameter space, okay. So this is my real line. You can observe these values, okay. Now what is the maximum of this? Let's say it is the x max here, and then your domain is like this to this, okay, up to infinity. So whatever the sample you get the accordingly you get this x max. So the parameter space changes depending on your sample data. Now what is my log n theta, log L theta? This is 1 by theta to the power n. So if I take the log, it is n times log of theta. I can take minus here. Okay, that's it. Now if I take d theta log L theta, if I take the derivative, because I am to find that this is n by theta, which is less than 0, because theta is positive and n is of course positive. So I get this less than 0. Okay, so this is then what you observe, that this derivative is a decreasing function, okay, of theta. Okay, so then what will happen? The domain is here x max to infinity. It is a decreasing function. So the maximum will occur, the max value will occur here because it is decreasing. Okay, because if you go beyond this point here, the value will decrease. So maximum only can get at this particular value. So then what is that you are getting? So then I conclude from this observation, conclude that theta hat equal to xn. Okay, I'm introducing this new notation. This is just to denote that this is x max. Okay, x max, maximum of x1, x2, xn. Or let me write it that xn to be equal to the max of x1, x2, dot dot dot. So xn. This we discussed as some problems before. So this is the estimator. Okay, xn. This is the standard notation. Actually, this standard notation comes from another topic, which is called order statistics, which I did not discuss. It is not part of the syllabus. So order statistics is regarding an ordering about the random variables. Okay, so random variables are functions. Now can we? So it is about ordering, means which one is bigger, which one is lesser, this kind of a thing. So max of this. So this is, there is the standard notation. This is this notation x, and then in the subscript we have n inside the first bracket, first parenthesis. Okay, so this is known as, let me just write it down, nth order statistic. So, you don't have to know this at this for this course. but if you're interested, you can get it in any book. Okay, order statistics. This is just a notation. Okay, xn. So which is the maximum of this. So then now see here, using for this, at least for the uniform distribution, theta hat equal to xn here. Okay, which is the maximum order statistic. Okay, or nth order statistic, and using ML, using ML, and using MOM, this was 2x bar. This was using what is called MOM. So then the question is, okay, then the question is, which one you will consider as the estimator? Okay, I am only talking about two methods. One is moment MOM, another one is maximum likelihood. But you can have other methods also. Using other methods, you may get different estimators also. Then the question is, there is a problem. And how do I choose my estimator? Because it depends on the method I choose. Depending on the method, I get an estimator. Okay? And the question will be, which one is good? Okay, whether this is good. Okay, xn, like nth order statistic, or the max of this x1, x2, xn, or it's just 2 times the sample mean, this one. Okay, so which one is better? And both the sample data, okay, here in this case, and this case, in both the cases, sample data is obtained from uniform, but I get 2 different estimators. Then the question will be, which one is the better one? Okay, so we'll discuss that now. But before that, let me just make a statement here, because normal is important. So let's say all these are normal population, x1, x2, xn, they are all some n mu sigma square, let's say. Okay, and they are IID from this. So if I take a random sample, then what is then this mu hat and sigma square hat? Okay, using ML. So we have done that for using MOM, and here if we apply maximum likelihood, you can check that we'll get the same estimators. At least for the normal, there is no problem. There is no difference in the estimators. Okay, for these 2 methods at least. So the solution you can find is that using ML, you'll get mu hat equal to x bar, and sigma square hat is equal to 1 by n, sum over I equal to 1 to n, xi minus x bar whole square. So there is no problem. Else for the case of normal, these 2 methods will give you the same estimators, but it is not a rule that you will always get the same estimators. The estimator can vary depending on your method. Okay, so then we discuss, okay, criteria, or let's say goodness. How to decide which one is good? Goodness of estimator. So which estimator is good estimator for a problem? Now here also there are different techniques to find out which one is better. So let me just phrase the problem here. Which one? Suppose we have 2 different estimators, because we have seen that can happen. It may be more than 2, depending on different methods. But since we have talked about only 2 methods, I can have maximum 2 different estimators. Okay, so which estimator is better? That's the question. So then better. Then the thing is, so basically we are trying to evaluate, okay, I mean the goodness of an estimator. Okay, now the thing is, even if in your real life, I mean in real life is our everyday life, how do I decide which one is better? If you go to buy potatoes, or if we go to buy some shirt or some pants, whatever, the dress, let's say, whatever, the TV, anything you want to buy, if you are given 2 things, okay, how do you check which one is better? So that means how do you check that? So what you do is you see the properties. I mean, in mathematical parameters properties, but in a language like, okay, which one you think that, so let's say potatoes, which suppose the potato is rotten or not, that is the thing, that is the question. So that's rotten thing is the property of the potato, right? So we need to check. So let's say television, okay, or do you want to go to a shop, you want to buy a television set. So now which one you want to buy? So there are different properties, or a mobile phone, whatever it is, okay? There are different features, there are different mechanisms, whatever it is. There are different companies, they have different architecture, okay, different looks, okay, outlooks, let's say, so whatever way, okay, so whatever you like. Okay, so basically, ultimately, at the end of the day, you look at the properties of this, properties of the thing which you are buying. So here also the same thing. So estimator must have certain properties. Okay, now based on that properties, we probably can evaluate which one is better. Okay, and there are different properties of this. We'll talk only about 3. I mean, not in detail, but just to give you an idea. Okay. So these properties include like unbiased. So I talked about that before. What is the meaning of unbiasedness? Okay, I mean, I did not define it formally, but I said we'll say it later. Unbiased, and then there is something called efficiency. In fact, it is called efficiency, okay, and relative efficiency, okay. Then there is called minimum variance, or let's say the exact term is uniform minimum variance. See, estimator end of the day is a random variable, so we have to check the properties of the random variable basically. And how do you check the properties of a random variable? You calculate mu, you calculate mean, variance, and some other things, right? So uniform minimum, that is called variance, unbiasedness. And there is one more called sufficiency, and another one is called consistency, and so on. So here, for the timing, I'll just define, or let me say, I'll just explain. I will not study, I will not discuss in detail, okay? So I'll only talk about unbiasedness, sufficiency, and consistency, because these are easy to handle. Easy in a sense that whatever we have discussed before, based on that, it is simpler to define. For these things, the other 2 things, or there are many more, I need to again introduce new concepts. So that's why I'm skipping that, 2nd and 3rd. So I'm only talking about unbiasedness, sufficiency, and consistency of an estimator. And all these 3 are introduced by Fisher. Fisher, the British statistician again. So these 3, the ticked 3, okay, are introduced. This, by Fisher, Ronald Fisher. Okay, so now I'll start talking about what is an unbiased estimator. Okay, remember what is an estimator. End of the day, estimator is a random variable because estimator because it is a statistic. Estimator. End of the day, it is a random variable, which is a function of this capital X1, capital X2, capital Xn. So function of this random sample. It is a random variable. So I have to study some properties of the random. Okay. This is the thing we have to recall, that this is, after all, end of the day, it's a random variable. The first thing is unbiased estimator. When do you call an estimator unbiased? Okay. Okay, so simply, let me just give you the definition itself. So theta hat, this is the estimator, is called unbiased if expectation of theta, since it is a random variable, I can talk about its expectation. Expectation is theta itself. Meaning what? Meaning whatever statistic I get for the estimator, let's say using normal, I said for mu hat is x bar, or for the uniform it is 2 times x bar. The for theta hat was 2 times x bar. Now this is a random variable, and its expected value, okay, expected value of this should be mu, theoretically. Then I'll say this is unbiased. Otherwise, I'll call it biased. Otherwise, we call it biased. It's a biased estimator. if it does not satisfy this. Okay. So then the question would be that the estimators which we discussed before, at least for the case for normal and for the uniform, are these biased estimators or unbiased estimators? That's the thing. So I'll not go into much more detail about why it is called bias, why the term bias is coming from. Does anybody have any guess why the word or the term, let's say, bias is coming into the picture? I mean, if it satisfies this one, I call it unbiased. Otherwise, I'll call it biased estimator. Why? Why I'm introducing, or people are official, let's say, are in this topic. Why do they call it bias? What is the guess? Okay, think about it. So this is all normal, let's say, random sample. And then we know that mu hat is equal to x bar. My question is it unbiased or biased? Is this biased or unbiased? Is this an unbiased estimator? That's the question. So what do you think? Huh? Who can tell me? It is unbiased, yeah, because expectation of x bar is mu. Okay, we discussed this before. Now we have theta square itself. So that's the second question. So not theta square, sigma square. This is equal to what? 1 by n according to according to ML or MOM. This is m I equal to 1 to n xi minus x bar. Don't forget that this is not sample variance because here it is n, not n minus 1. And when I introduced the concept sample variance, I said that why do you call it, why do you take it n minus 1, not n? Okay. Anyway, so now the question is this biased or unbiased?
Biased, sir.
This is biased. Estimation, expectation of sigma hat square will be what? Expectation of 1 by n, sum 1 to n, xi minus x bar whole square. Okay. Now, what is the expectation of this? Okay, I'm just doing this calculation because this calculation will give you, will recall some of the things which we discussed that will relate to those things. So this can be written as E, because see, if I want to calculate expectation, I'm looking for a very standard specific distribution which I can use in order to calculate this value. Okay, I'm trying to find that. Okay, so because otherwise it will be a lot of calculation. So what I do, I can take this as this, I mean time 1 by n minus 1, because I know that there is s square which is related to this, so square of this one. Okay, so then expectation of this n minus 1 by n will come out. This is property of expectation. Then expectation of this is what? This is just this, and this is nothing but s square. Okay, the sample variance. But for the sample variance s square, do I know anything about s square? Whether this is expected, this s square, okay, is related to some distribution, some standard distribution, which is a function of this s square. Recall, n minus 1 by sigma square is nothing but chi-square when this random sample are all drawn from normal. So I'm going to use this property here. So this one is n minus 1 n times E of, okay, n minus 1 times sigma square. Then I have to take n minus 1 out, and then I have to multiply sigma square here, which is what? Internet gone. Guys, can you hear me?
Sir. Yes, sir, we can hear you, sir.
Guys, can you hear me now?
Yes, sir.
Yes, sir.
There was an internet problem. The internet was gone. Anyway. Okay. Yeah. So here now, can you see the screen? Oh, I have to share it again. Just a minute. Can you see the screen now?
Yes, sir.
Yeah. So I was recalling this, that we know that when the random sample is from normal, and n minus 1 by sigma square times s square is chi square with n minus 1 degrees of freedom. We proved that. A simple proof. So here I have expectation of s square. So I'm taking that. So if I want to do n minus 1, so I have to put this inside this here again, and I have to multiply sigma square. So I put that inside, and I multiply it with sigma square. So in the denominator now I have sigma square. So this is sigma square by n times expectation of this. So this is chi square n minus 1. For chi square, I know that expectation of this is, and the mean of this is nothing but the degrees of freedom. So here it is sigma square by n times n minus 1. And this is not equal to sigma square. So expected value of this estimator, okay, of this estimator is not the parameter itself. The parameter was sigma square. So it is a biased estimator. Okay. So it is, so I would say sigma square hat is a biased estimator. Biased estimator. It's not unbiased. At least we have seen now that the estimator which we have found using ML or MOM, they are for the case of sigma square, in the case of normal population or normal random sample, it is biased. Okay. In fact, there is a more general thing. Okay, this I'll state as a problem. I'll not prove it, but you can try to prove it. That it does not only depend on normal. It is always the case for any population that S square is an unbiased estimator for the population variance sigma square. So what I'm saying is, it does not matter if it is normal or not. So this is what I said. So this is a biased estimator. Okay. What is biased estimator? When you take this to be n, this to be n, it is biased estimator. This is the estimator which I got using ML or MOM. This is biased estimator. But if you consider S square, okay, why did we define this not to be n but n minus 1? I am justifying this now. When I defined it, I said I will justify it later, something called unbiased. So here I'm justifying it now. It does not matter whether it is normal or not. For any population, S square, the way we defined 1 by n minus 1 instead of 1 by n here, it is always an unbiased estimator, independent of the population. So if it is x1, x2, xn, let's say it's a random sample from x with some mean mu and variance sigma square, which is positive, then S square, you can prove it. S square is an unbiased estimator. What is S square? Okay, I'll just recall unbiased estimator for the population variance, for the population variance sigma square. So this is a general thing. So my remark here is Okay, here, and it does this result does not depend on the PDF of X. It could be any PDF, does not matter. That's why we define sample variance like S square, which is 1 by n minus 1, sum over xi minus x bar whole square I equal to 1 to n. So the question was, when I was defining mean, it was 1 by n. That is natural thing to do. But when we defined sample variance, this statistic, instead of taking the average of these values, the distance, okay, or the mean squares, so this is the mean of the squares. Some sort is called mean square. I mean, if we just represent minus 1 by n, okay. So I am not writing n minus 1, but I am defining sample variance. I defined rather before that's the variance. The sample variance is 1 by n minus 1 times this. So the reason being, doesn't matter what the population is, this is always an unbiased estimator for the population variance. Guys, can you hear me?
Yes, sir.
Okay.
Yes, sir.
So, okay, I thought the internet is gone again. Anyway, so this is very, very important. Okay, this is an important observation. That's why now, so here, let me just say that hence we have justified the definition of sample variance. That why do we take n minus 1 instead of n? Now here it is very interesting also to observe, at least for the case of normal, both MOM and MLE, they give you a biased estimator for the variance. Okay, they are not unbiased, which is a property of the estimator. Okay, so this is one property of the estimator. Now I'll talk about another property, and why I'll also talk about that. So I'll define why when an estimator is called sufficient. Now, the problem with this property, biasness, is that you do not know theta, right? You do not know theta because that is the population parameter. So there is no way to check whether this is true or not. Okay. So you have a guess about the distribution of the population. Let's say normal. So normal has two parameters, mu and sigma. Okay. Now for mu you can find out an estimator. For sigma you can find out a sigma square. You can find out an estimator. But you cannot check this because you do not know the value of theta. Theoretically, if you know the value of theta, the parameter itself, let's say, then you can check that you found this statistic, you compute its expectation, and you check whether it is equal to theta or not. So there is actually no way to check whether an estimator theta hat is biased or unbiased. So this is a criteria, but there is a problem with this criteria. So that means we need to define some other criteria to judge, okay, the quality or some characteristic of the estimator. And sufficiency is another criteria to judge, okay, the quality of an estimator. So that's why I need to introduce this estimator, okay. Now recall here that we want to find the estimator for any using the method MOM or ML, okay. But that estimator should be independent of the parameter theta, because estimator is a statistic which is a function of x1, x2, xn. Okay, there is no theta involved here. Okay, we said it before. Okay, now from that perspective, we are defining what is called a sufficient estimator. Okay, this is my definition. So here, let's say again the same thing, that we have a population random variable, which is capital X, which has the distribution this, and here theta is unknown. And x1, x2, xn is a random sample. So they have their IIDs. Okay. size. This is a random sample of size n. Then theta hat is called sufficient estimator. It's called a sufficient estimator if the conditional let me write it. The conditional distribution of the sample, of the random sample, given the value of theta hat value of theta hat does not depend on theta. Now, what is the meaning of this? I mean, so see, now what is the PDF of a random sample? The PDF is that I have x1, x2, dot, 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 xn. This is all independent, x1, x2, xn. So, and each of this xi has the same distribution as xs, okay? And then I can take the product of those distributions in order to get the the PDF of this. Now what I'm saying is, this is the PDF. And I know, suppose the estimator theta hat, this will be some value based on your sample data. So, and if I don't talk about the sample data, then this is just a random variable. So given this theta hat, so then I have this distribution. It's the conditional distribution. The theta hat is known. Then what is the PDF of this? So in the PDF, wherever this theta hat I can replace that after knowing this. Then this has to be, this is now a function. It has to be independent of theta. Then it is called a sufficient. Okay. Now, there is a problem. The problem is that I do not know, okay, that what is the density of my x. Okay. And I just have a guess. Second thing is, this could be any function of x1, x2, xn. And I do not know the PDF of this estimation, this estimator. See, how do I calculate conditional? PDF of this, f of, let's say, x given y. How did you do that? This is f y by f of y, right? This is how we defined it before, conditional density. But this is not known to, so I can say xy, and then f of y, y. So this is denominator is the PDF of the estimator here. But the density of the estimator is not known. Or maybe it could be a very complicated function. Because it is a function of x1, x2, x3. Somehow if it is a simple thing like x bar or s square, then I can find it out. But in general, okay, for example, all its xi's are normal. Then I know what is this PDF of x bar, the mean, sample mean, or the variance, s square, I know that. But if it is a complicated function, I do not know what is the PDF of theta hat. Okay, so it is not easy to find. So I cannot find out what is this, and I cannot check whether it is independent of theta or not. So in order to avoid that, there is a theorem which is known as factorization theorem. Okay, this is again by Fisher and one of his collaborator, I think Niemann, his name was Niemann. Okay, let me just state the theorem. What does it say? It is a very, handy. There is a very handy result which is given by this theorem. Okay, this theorem says, this theorem is due to Fisher and Niemann. Using this theorem, we can check whether an estimator is sufficient or not. So here, so let's say we have x1, x2, xn. This is the random sample. And we have this if the joint this x1, x2 dot 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 xn and then theta. I'm writing a semicolon here again because theta is the parameter. This depends on, because the theta is here, this depends on the parameter theta. Then theta hat estimator for theta is sufficient if and only if this distribution, this joint distribution is, this can be factored as this, a function of theta hat times a function of x1, x2, xn. So where phi depends. So this theta hat is again a function of x1, x2, xn. So this depends on x1, x2, xn only through theta hat, and h, this function x1, x2, xn is independent of theta. Independent of theta. So if this joint distribution can be factored, I'll see an example. I'll show you an example. And only one example because we don't have much time to do. So this is a product of two functions. So one is a function of theta hat and theta. Other one is a function of x1, x2, xn, which is, and this h, this function is independent of theta. Then this theta hat is a sufficient statistic. Okay, so then it will imply, I'm not proving this. So this conditional distribution is independent of theta. Okay, so let me just see an example. Okay, let me just show you an example. So let's say I have a random sample, okay, which are all from normal, okay, normal distribution, okay, with parameter mu. So sigma square, I'm putting some values. Okay, can you guess what is the value of sigma I'm putting here? So if x mu is this 1 by square root of 2 pi to the power minus half x minus mu whole square. What is the value of sigma square here? If it is normal, guys, can you hear me?
Yes, sir.
So what is the value of theta here? Sorry, sigma square here. If it is normal, what is the value of sigma square? What is the distribution of normal? What is the formula for normal distribution? Anybody? Huh?
1, sir.
1. Okay. 1. So this is from the normal population. Now I have to check whether mu hat is sufficient estimator or not. What was my mu hat? Mu hat, this estimator. Okay, mu hat. What is mu hat? Let's say according to ML, what is mu hat? What is the estimator for mu in the case of normal using ML? Or let's say MOM.
Mu itself.
Huh?
The
X bar.
mean itself. Yes.
Yeah, so mean is a parameter, but I need to have a statistic. So this is X bar. Okay. The function of x1, x2. Now, let us first, I will check that this is actually a sufficient statistic, a sufficient estimator using this factorization. Okay. Now, here the function, the parameter is mu. Okay. So this joint distribution x1, x2 dot 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 xn mu is what? This is a product of I equal to 1 to n f of xi mu. Okay, xi mu, which is what? I equal to 1 to n 1 by square root of 2 pi e to the power minus half xi minus mu whole square. The product of this, same thing. So this scalar 2 pi to the power n times e to the power. If you take the product, exponential, it will be sum half sum over I equal to 1 to n xi minus mu whole square. Then this can be written as 1 by, I want to factorize this in terms of this, okay, in terms of this kind of a function. So mu hat, mu function, which is phi, and another is only depends on another function, which only depends on x1, x2, xn. So this is, it is just an algebraic manipulation, but in some cases it could be a difficult problem, but here at least for the case of normal, it is easy. So keeping that in mind, let me, so I have to somehow bring in x bar, okay, because x bar is the estimator. So 1 by 2 and then sum over I equal to 1 to n, I can write this as xi minus x bar plus x bar minus mu whole square. So then this will give me 1 by square root of 2 pi to the power n e to the power minus half sum over I equal to 1 to n, and then xi minus x bar whole square plus 2 times x bar minus x bar times x bar minus mu plus x bar minus mu whole square. Okay, this is the formula of a plus b whole square. Okay, so then this equal to 1 by square root of 2 pi for n. Then what can you say? Any idea? What next? I want to factorize this as a function of mu and mu hat and mu, and times some function of x1, x2, xn. So how do I do that? So I want to write it like this. Okay, so how do I do that?
Separate the terms of xi, x bar, and mu.
Okay, and then see here I have to somehow get rid of this term, the second term here. Can I get rid of this term somehow? Yes, if this term is here, I cannot separate it out from xi's and mu. So here, mu is not here, it's just xi's are here. Somehow I have to get rid of this xi's and mu. So what do you do? Should I give it a homework? Just one more step, that's it. One more trick will do this. How do I do it? Anybody, any idea? Mu is a parameter which is not known to me. Xi's, small xi's are known to me. Hence, small x bar is known to me. Okay. Anybody, any idea? Okay, I'm leaving it as homework. One more step will do this and think about it. Okay. Okay, now, okay, now I'll introduce one example and that's it. Then I'll talk about another property of estimator, which is known as consistent estimator. What is called an consistent estimator? And here, now see here, we started talking about x1, x2, xn, and using different methods, we can find out different estimators. And not only that, even if you fix the method, depend on n, okay, your estimator will change. Estimator will change means the value of the estimator will change. How do you estimate theta? For example, x bar, okay, is sum over all this, let's say, xi's. Suppose this is the estimation for some parameter, let's say mu, for the case of normal. But I equal to 1 to 2 could be different value, I equal to 1 to 3 could be a different value, I equal to 4 could be a different value. So the estimator, the way you are estimating the value for the parameter also depends on the size of the sample. So this is the crucial observation. Okay. Note that the estimator depends on the, by the way, if somebody is studying, let's say interested to do machine learning or data science later on, there will be many occasions where people will assume that the statistic is sufficient. And here it is the meaning of the sufficient. Okay. This is the meaning of the sufficient statistic, sufficient estimator. So sometimes people will assume that you are considering a statistic which is sufficient. That means it has to have this property. Estimator is a statistic and this has this particular property. Okay, so know that the estimator depends on the sample size n. Okay, because of this way. So if I take I equal to 2, it will give me something. I equal to 3, it will give me something. So obviously the way you are estimating the unknown parameter theta, that will change, and that will depend on the value of n. So now instead of writing theta hat as an estimator, we'll write theta hat n. That means, so this is the new notation for estimator. That means how many sample data you are using to estimate your parameter. Okay, if you are using n, then it is theta hat n. So n could be equal to 2, 3, 4, 10, 100, whatever it is. Okay, so this estimator depends on the value of n. Now I am coming to the definition of consistent estimator. So then different. So you can see here you are as if you are creating a sequence of estimators. Example, you take 2 sample data, you get an estimator. 3 sample data, 4 sample data. Okay, these are all, they'll get some values about the unknown parameter theta you will get, and this goes on. Okay, depending on different values of n. So this is a sequence now. Now we'll say some property about this sequence, and then that will help us to define what is called consistent. Okay. Okay. So let me just define it. So here I am assuming that x1, x2, dot, 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 xn is a random sample from x. Then I'm saying that a sequence of estimators theta hat n, this is notation for sequence, estimator for theta or of theta is said to be consistent. Okay, if and only if the sequence theta n or theta hat n, this converges in probability, which we defined before 2 weeks back, converges in probability to theta. So what is the definition? What was the definition? For any theta, for any epsilon, limit n goes to infinity, probability that theta n hat minus theta is bigger or equal to epsilon is equal to 0. So sometimes we'll denote it as that theta hat n p theta. So this is standard notation for sequence, a sequence theta hat n, or any sequence whenever. So I discussed that this definition of convergence is different from the standard definition of convergence of a sequence. If you have a sequence xn, sequence of numbers, whatever the numbers are, so this will converge to x in probability, then I'll write the notation as this p. The meaning is this one. The probability that when n is large, probability that the value of theta will be far from theta in hat. Okay, far from means it is at least some distance epsilon far. That will happen with probability 0. So that means theta n, when n is large, theta hat n will be close to theta. Okay, this is in terms of probability. Then this is called a consistent estimator, a consistent sequence of estimators. And in fact, okay, consistency, okay, for a large sample, okay, so because I'm taking theta n tends to infinity, so it's a property of the estimator when the sample is large. Okay. Now the question is again, how do you check, given some theta n, how do you check that where does it converge? Because theta is unknown. Okay, or maybe you're known, for example, I mean anyway, so let me just say that for the case of normal x1 x2 xn, okay, which is, let's say, normal means sigma square, then sigma square hat is consistent. Is it consistent? That's the question. Is it a consistent parameter? Yes, it is a consistent estimator. Consistent estimator of sigma square. So here I'm not deriving any more proper. I mean, I'm not giving you the proof because let us skip the proof. We are running out of time. Okay, so let us skip the proof and then let us go to the big topic, which is here. Now see, so these are the property of the estimators. Okay, but anyway, ultimately, I mean, if you don't know this sufficiency, unbiasedness, at least you should know unbiasedness, and this one, sufficiency and consistency. But anyway, end of the day, what are you doing? End of the day, I'm estimating the population parameter. Okay, using some method, finding an estimator. Okay, this is what I'm doing. An estimator has certain properties, like whether it is sufficient, is it consistent, this is unbiased, this kind of thing. That is, all these are theoretical. Okay, unless you know that the distribution and this and what is the sample size, you cannot talk about all this. Okay, so anyway, so but these are the properties of the estimator. But the question is, if you use this kind of estimators using this kind of method, ultimately what you are doing is we are giving a point value. That means suppose the value of the parameter is 5. Now I am estimating this 5 by using this random sample or the sample data by, let's say, 3, 3.5, 4, 4.5, 4.9, whatever I get, I am estimating that. So there, since I do not know the original value of the parameter, the original value means the population, I do not know the exact value of the population. In general, it is very difficult how much far I am estimating for. So what is the accuracy? What is the accuracy of my estimation? Okay, I cannot make any comment on that. Okay, in fact, I will give you an example. Let's say, so I mean, the crux of the matter is, what I'm trying to convey to you is that sometimes it may give you a very bad estimation. That may happen. So in order to avoid that, what we'll now study is something called interval estimation. So instead of point estimation, okay, I'll now talk about interval estimation. Okay, interval estimation. Interval estimation. So before I talk about that, let us consider a simple, let's say, observation. Okay. Let us say that I have a random sample, x1, x2, xn, from a population, let's say X. Okay. Our PDF is, let's say, something like x theta, which is the square root of 2 by pi, e power minus half, x minus theta whole square, x is bigger equal to theta and 0 otherwise. A very simple, nice formula. Then if I want to find an estimator for theta, okay, then what I have to do, suppose I have to use maximum likelihood estimator, okay, then you can find it out, okay, and you will actually find, if you do it, so this is again homework, you'll see that theta hat is nothing but x1. So x1 is what? Which is minimum of x1, x2, xn. I'm just, for the sake of calculation, I'm just giving it to you with this example. I mean, it is very simple to find out this estimator value. It is just the minimum of all this, x1, x2, xn. Now, suppose the true value is, suppose the true, which I don't know. So suppose the true value is theta equal to 1. Now, what we are trying to do, using this estimator, okay, using this estimator, okay, I mean, why I'm taking this example, I could have taken it normal and something. So this is kind of normal, but the scaling only is different. Why I'm taking this? Because for easy calculation, nothing else. Okay, you can try with any kind of a PDF and you can check it out. Okay, so suppose my true value is theta equal to 1. I can have that. Then this is a PDF. Okay, this value is this theta. Now, what I'm trying to do is, using this theta hat, I'm trying to make a guess about theta equal to 1. Okay. Now, suppose x1 is a small x1 is 1.5, x2 is 1.1, x3 is 1.7, x4 is 2.1, x5 is 3.1. Suppose this is my sample data. Then based on this sample data, my theta hat value is x1, which is mean of all this, so which is 1.1. Okay, so this is my estimated value for theta. I can have another sample. Okay, for another sample, I can have x1 to be equal to 1.8, x2 to be equal to 2.1, x3 to be equal to 2.5, x4 equal to 3.1, x5 equal to 2.6, and so on. Then if I use my estimator, okay, then this value will be minimum 1, which is 1.8, based on this sample. Okay, so now if I plot this, function, okay, if I plot this function, I'll see that this plot will look like this. For theta equal to 1, this is my original value. Okay, so this is that x, this is an exponential function, so it is kind of this, theta equal to 1. Let's say this theta equal to 1, so it will gradually decrease. Okay, so it is like this. This is for theta equal to 1. Let's say. Now this is the PDF. Okay, this is my PDF. I have different values from here, sample values. Okay, I'm getting some values from here, but I do not know the value of theta. The original value is theta equal to 1. I got a sample where in the first case I got this sample, I get this value estimator, which is 1.1. Here another estimator is 1.8, and so on. Now see here from the graph, what you can see, the graph, it is clear that if you take a value number which is close to 1, there is a high chance, because the probability is high. Okay, probability is very, very high here. This is a PDF, so this is x and this is fx. So this is a high chance that when I'm sampling out these values, and there's a high chance that I'll get a value which is close to 1. Okay, I am getting some values from here, but these values will come with some probabilities. But anyway, probability of having a single point is 0 always, because it is continuous distribution. But for the sake, looking at the probability, what I can say, that I will get a value close to, that's what I'm saying, in the interval of 1, close to 1. This value is, let's say, 1, theta equal to 1. So close to 1. So that is, x equal to 1. Suppose I get a value which is close to theta equal to 1. So then there is a high chance to get it. Okay. So it makes sense that if you take higher values of the random sample, if you say 10 samples or 100 samples, there is a chance that the sample values will spread over all the place. So here the observation is that this theta should be estimated by the smallest sample value. Okay, but this is not a true value, as we have seen. Even if you take many samples, okay. So this is a homework again. That you use Python, for example. It's Python. Okay, to do this exercise, meaning use Python to sample data from a distribution. Let's say it is uniform, normal, and use all this estimator which I'm talking about in this course, and see using the sampled value how good, okay, how much better they are estimating, let's say, the true value of theta. You know the true value, why? Because you have generated the random sum. So if you write a comment in Python, okay, it will generate a distribution with the given parameter values. Okay, now you pick out a random sample out of it. There is a way to do that. Okay, this is an inbuilt function in Python. You can do, you just search it in Google. You can get a sample, some sample points. Now once you do that, then you using that estimator, whatever we have talked about here, for let's say for the case of mu sigma square, for the case of normal, or for the case of uniform, use theta. Okay, so you just check whether this estimator is giving a good estimation for the true values. Okay, so now the question here is, okay, it is expected also, you can see that it will not give you a good value, but it will give you a true value, but it will give you a value which is close to that. Okay, close to that original value theta. Then the question comes, okay, now whenever you are estimating this, how much confident you are about your estimation. Okay, so this question of confidence interval, now it is like, what is your degree of confidence about the values of theta that you are producing using your estimator? This concept is called confidence interval for the parameters, or interval estimators. Okay, so now we'll talk about interval estimator. I'm running out of time. So what is an interval estimator? You have a value theta, which is a parameter. We are trying to estimate this value. Okay, now I'm saying that, okay, if I give you a kind of an interval, that will be a better estimation. But in that case, you also have to say, okay, with how much confidence you are giving this interval. Okay. Now, for the case of point estimation, that means what we discussed before, I have to give an estimator, means I have to produce a statistic, some t of x1, x2, xn, okay, which is theta hat, in order to estimate theta. Now I am looking for two statistics because I have to give an interval. So the idea is, given a random sample, let's say x1, x2, xn from a population X, okay, and a probability, given this and a probability, probability 1 minus alpha. So I'm not writing it alpha. There is a reason to it. Okay. So the value of alpha is also lying between 0 to 1. Okay. So with the probability value 1 minus alpha, find a pair of statistics. A pair of statistics. Okay. Let's say L is the lower bound. L x1. This is statistic is a function of x1 x2 xn. And U, it is again a function of x1 x2 xn. And L has to be less than or equal to U. When it is equal, that means it is point estimation, such that the probability of theta being inside this, okay, is 1 minus alpha. So what I'm trying to say, what I'm trying to tell you is probability that this theta is lying between these two values is equal to 1 minus alpha. This is the problem of interval estimation. Okay, so what we have a sample data. What is sample data? Small xn, small x2, small xn. And we have a guess about our population distribution f of x theta. Okay, then what is the interval estimator? Interval estimator is now the pair of statistics L and theta, L and U, that has these properties, that satisfy this property. So that means I can say that if we have, let's say, x1, this is your sample, then theta should belong to L of these values, x1, x2, small xn, comma, U of x1, x2, xn. So this is L and U that you have to estimate with some confidence. Okay, now I will define what is the confidence here with some probability. Okay, now I have to define what is the confidence here. So the interval estimator, like L theta, interval estimator of theta is called a 100 times 1 minus alpha percentage confidence interval for theta if the thing I discussed, L less equal to theta less equal to U, this is theta is equal to U is equal to 1 minus alpha. And this L is called lower confidence limit. And this is called upper confidence limit. Okay, and 1 minus alpha, this is called the confidence coefficient or the degree of confidence. Note that this has to be probability 1 minus alpha. Okay, then alpha is called, 1 minus alpha is called the degree of confidence. 1 minus alpha is called the degree of confidence. Oh, here also I have it. Degree of confidence. Okay, so basically you have this x1, x2, xn, and again you have here, instead of one statistic, you have to produce two statistics, such that this parameter value is lying between this L and U. The statistics are L and U, and the probability that the parameter is lying between L and U is 1 minus alpha. And here also the same thing. There are different ways to construct confidence intervals. Okay. So for example, there is called methods. How do you find, like MOM and ML, like moment method and maximum likelihood method. Here also different methods to produce this confidence interval. I'll discuss only two. One is pivotal quantity method, and another one is MLE. Another one is maximum likelihood estimator. Okay. Okay. So first, let us discuss pivotal quantity method. Okay. Pivotal quantity method. Now here you will see that we have very limited knowledge about dealing with data. Okay. I mean, these methods are okay, but for a general problem, okay, this method may not work very well. I mean, say when you were in, let's say, 10+2 standard, then your job was, given a problem, how to solve the problem, okay, or how quickly solve the problem. Okay. Now, when you get into here in Math 1 and Math 2, you must have understood that all problems may not be solvable. There are methods to solve certain problems, okay, but it could be difficult to solve the problem. Now here in this course, we have come to a situation, even there are methods to solve the problem, that methods need not work. So you have to design methods depending on the problem itself. So here you see now that life is very complex. Okay, life is not simple. Given a data, you have to make some conclusion about the population. Okay, it's hard. It's not a simple problem. As we have seen before, that if you want to estimate this theta, then we try to do point estimation. Then we have different properties of estimators. Now we are saying that we don't want to do point estimation. We want to do confidence interval, or we just want to interval estimator, okay, with some confidence. Okay, and then there are methods to do that, and this method also may not work. Okay, so we are getting into a challenging situation in real life. Okay, so not everything is very simple and not everything is possible. There are things which are very hard to do. I would not say impossible, but it's very hard to get. Okay, so and that's why we need to put some time, some effort to develop new methods to solve new problems and so on. Okay. Anyway, so here let us now talk about pivotal quantity method. So here is my definition. Okay, I'll just, because we don't have much time, only we have next like tomorrow, and that's it. So let's say I have this x1, x2, xn. This is a random size. I have this a random sample of size n from x with some density function fx theta. Okay, then a pivotal quantity q is a function. This is very interesting function. This is a function of x1, x2, xn and theta. Okay, what is theta? This is distribution is f x theta. Theta is the unknown parameter. This is a function of x1, x2, xn and theta, whose PDF was probability distribution. Let's say probability distribution is independent of theta. Independent of the parameter theta. This is very interesting. It's a function of x1, x2, xn and theta. Okay, but its PDF is independent of theta. Okay. Now, so pivotal quantity basically will contain the parameter theta and a function of x1, x2, xn. So it is a statistic. Okay, so it's a statistic of theta, because again theta can be estimated using x1, x2, xn. Okay, so let us see an example. So let us say x1, x2, xn. This is our form normal with mu sigma square. Now my question is, find a pivotal quantity. Okay, are you aware of the word pivot? Or first time you are hearing this? Pivot, you see, when you solve linear system using Gaussian elimination, there is the concept of pivot. So pivot has an English meaning. So pivotal means it is prime, nothing else. Okay. So pivotal quantity for the unknown by theta. How do you find it? That means you have to find a function of xi's, which are normal distributions, and the parameter is mu. So you have to find a function of this. Okay, but its distribution is independent of mu. Now here, for example, you see x bar. If xi's are normal, then what is x bar? What is the distribution of x bar?
Normal.
Yes, normal. What is the mean and variance? This is mu and sigma square by n. Now, since x bar is this, then what is x bar minus mu by sigma by root n? What is this distribution? So x bar is normal, and this is a standardization of the normal. So what is that?
Normal, standard normal.
Yeah, it is standard normal. Now see, this is the function here, qx1, x2, xn mu. This is a function of xi's and mu, but its distribution is standard normal, which is independent of mu. Okay, so this is the pivotal quantity of x1, x2, xn, and mu. So here I'm saying it again. What is pivotal quantity of the parameter theta? So you have a random sample x1, x2, xn. So this is a function of x1, x2, xn, and theta, but its PDF is independent of theta. So here xi's are normal, mu sigma square. You got a function, which is this one. This is a function of x on x2, xn and mu. Why is x1, x2, xn? Because x bar is this. Only and sum over this xi's. I equal to 1 to n. So it is a function of xi's and mu, both. But its distribution, its PDF is normal, standard normal, hence it is independent of mu. So this is a pivotal quantity. But this is a simple example. Okay. In fact, there is no, I should write this as a remark. How to get a pivotal quantity? So remark is that there is no way. There is no general way. You can find some examples, but there is no general rule. There is no general rule to find pivotal quantity for some distribution. Pivotal quantity for f of x theta. Okay, but up to certain extent you can find it. Certain extent for some nice functions, some nice density functions, you can actually find it. Okay, and this is now the class I'll define those set of nice functions. In fact, now see here, I asked you a question long back. I said, we are studying the specific distributions like Poisson, normal, binomial, this and that, gamma, beta, okay, Cauchy, and this kind of things, because they arise in real life and they are very nice. But in which sense they are nice, now it will come. Okay, in which sense this is nice? Because if the population has this kind of a distribution, then I can probably find this pivotal quantity easily. Okay, or my guess will work. Instead of any general density function, if I have a density function from this kind of a class, then possibly I'll be able to find it out. Okay, so here I'm now justifying why we study this fundamental density functions in the beginning, because they are nice. In what sense they are nice? One of the reasons is this one. This is the definition. So the definition is let G R toward be a PDF. Okay, guys, just give me a minute. Somebody's knocking. Okay, so I'll end this lecture with this definition. Okay, so let G be a PDF, then for any mu and sigma positive, the family of functions, let me define this f as the function. This is this function x mu sigma. See, mu sigma is nothing to do with mean and variance. I am denoting this mu and sigma due to something. Okay, they can be any constant. You can write just a b, not a problem. But I'm defining, so G is a PDF. Okay, now I'm defining a new function using the PDF, which is this 1 by sigma times G of x minus mu by sigma, where mu could be anything. Mu is lying between minus infinity to infinity, and sigma is positive. So sigma is positive. So this class of functions given a PDF G is called the location scale family. Location scale family with standard probability density f of x theta, and mu, the parameter, is called location parameter. See, in some books, I said it before also, in some books they define these density functions like say gamma, the beta. So there are two parameters. One they call location, another one they call scale. Okay, so here this is the reason I'm giving now. I did not define it this way. I just said, okay, you have two parameters. One parameter reflects that how much it is scaled, and one parameter depends on like what is the shape of the parameter. So I call it shape and scale parameter. So here I'm calling location. There is a reason to do that. And sigma is called a scale parameter. So if you just take only one constant, not two constant, mu and sigma, but let's say just fix sigma to be equal to 1, then f is called location family, and if mu is equal to 0, why sigma is equal to 1? Sigma has to be positive because it is 1 by sigma is here. Okay, I cannot take sigma to be equal to 0. Or from the perspective, you can make a guess from the normal distribution. Sigma is 1 and mu is equal to 0 standard normal. So if mu is 0, then f is called the scale family. Yeah, I'll stop it here. So my goal is, why I'm introducing this, when I have density functions which look like this. So that's a scaling of a density function, but the argument is a little different. It's a translation and scaling. So that's why I call it standardized version in the beginning. X minus mu by sigma. So here mu sigma need not be mean. It could be any constant. But from normal to standard normal, we do this. X minus mu by sigma. Okay. So square root of sigma square basically. So anyway, so I'll show that, I mean, why I'm introducing this function. If you have a PDF which is belonging to this class of functions, for those functions, this pivotal quantity function is easy to find. Okay. In fact, I'll show you that most of the density functions which we talked about are in this class, and one of them is normal. Normal is also here in this class. Okay, we'll do that tomorrow probably. Okay, so let us stop here. So you can leave the class, and if you have any questions, you please ask. I stop the record.
Yes.